Cheshmi, assistant professor at McMaster University, who is going to talk about loop fusion in matrix multiplications with sparse dependence.
Thank you, Amit, for the introduction, and good morning, everyone. I'm presenting loop fusion in matrix multiplication with a sparse dependence. The work is led by my PhD student at McMaster, which I'm presenting on his behalf. The consecutive matrix multiplication, which is the focus of fusion in this work, often happens in many applications, which I listed some of them in here. Well, I'm starting with the graph neural network as an example throughout this presentation. That's why I'm explaining, I'm showing the closed form of one layer of graph neural network here. Particularly, this is a graph convolutional network. So in graph neural network, it's a type of neural network that operates on graphs. So like, as you can see, in one layer, we have two pair of multiplication, like multiplying matrix A with H, and then H with L, or the result of that with W, which is the weight matrix. And then this is a ReLU will be applied for each layer. So here you can see a few pair of operations, and I'm listing two of them, which is actually interesting for this presentation. One of them is we have dense matrix multiplication, which I use gem from here on because it's pretty long, and followed by a ReLU. And then the other pair that you can see is two matrix multiplication, as you can see, A times H, and the results times W. So as you can imagine, there are lots of data exchanged between these two pair of operations, and if you want to reuse those data, the solution is fusion. We are all familiar with that. And to start explaining the idea and how the fusion helps data movement, I will start with the simple case of ReLU, gem with ReLU. As you can see in this slide, I'm showing a matrix multiplication, which is shown with triply nested loop at the top, and then the ReLU operation, which is an element-wise operation, goes over the matrix and apply the ReLU in each element. So ideally, the D matrix that is created here, it's a common between them. So if you want to visualize this, the green colors here are the locations that will be accessed to compute one row of D1, which is shown with blue, and then the same row will be reused in the next operation and stored, and finally we can compute the row at the final results D. So if we want to reuse this element D, we want to fuse these two loops, as is shown on the right-hand side. Very simply, we fuse the I1 with J1, and then we have the loop on the right-hand side where the accesses to the intermediate matrix now are very close to each other. So that's going to stay in the cache, and we can reuse the cache information. Of course, there are so many other ways to fuse gem with ReLU, but that's not the focus. This is just for illustrating the point of fusion, which actually allows us to reuse the data, in this case, in the cache. So that's actually a very nice transformation that can improve locality. What about the gem? Let's say we have two matrix multiplication back to back, and we have this, again, V1 matrix intermediate result. We want to use them. How can we actually do that fusion? Let's look at the code again. Here we have D1 shared between both of them, and if we want to follow the same approach that I just discussed, we can just simply fuse the outermost loop of these two operations, and we get the code on the right-hand side, and again, we are getting reuse on D. Well, that's actually reuse happens, but unfortunately the results is not correct, because the second operation, one after fusion, will get the incomplete results from the D1, and that's why we are getting the wrong results, because in other words, we are violating some dependence after fusing these two. Let me explain this visually, so actually it becomes more clear, since I need this example throughout this presentation. So here I'm showing the wrong fuse code, and again, in the first matrix multiplication, you see the green color that shows where it's access to compute one row of the intermediate matrix D1. And if we want to use that row to compute one row of the final matrix D, we need actually those red locations, which is not calculated in the first after fusing these two operations, and that's why we are getting the wrong results. So the reason for that is because of what we call dense dependence. So in order to compute one row of D, we need to compute every single row of the intermediate matrix D1. And that's what we call dense dependence. Now let's actually make our assumption a bit more realistic by assuming that matrix A is sparse, which is the case in many applications, including the GCN that is the focus here, at least for this presentation. So here, instead of having that dense A, we have this sparse A, which some of the elements are removed, like basically because those are zeros. So now if we do the same thing again, compute the first row of D1, so we have, can we do the multiplication? Still, we can't do much with that. But if we compute the second row of the D1, basically if you compute one tile of D1, which is with size 2, and then we can use that 2 row to compute the 2 rows of D, the final matrix, correctly. And the reason for that is because we have 2 zeros in the second and those 2 columns on matrix A, and that sparsity allows us to fuse, basically to reuse this partial reuse between tiles, basically that tile D1 and a final tile D. This is what we call a sparse dependence, because for computing the 2 rows in D, we don't really need to compute all rows of the intermediate matrix. Well, the question is, well, that's a nice feature to have, but is it realistic? We indeed did this investigation to compute the reuse, the percentage of operations that share data on the y-axis, and the x-axis shows the list of switch sparse matrices sorted by density. We indeed compute the share data reuse between these 2 operations, let's say between gem and SPMM, to see how much it is realistic to actually focus on this fusion. And we found that actually this property naturally exists in many of these matrices. Well, even if it doesn't, you can apply reordering, but that's, again, I don't want to talk about that in here. So with that property, we actually had motivated our work to focus and come up with a system that actually benefits from this partial fusion, and that's what we call tile fusion. So we propose tile fusion that has 2 components, compile time and runtime, and basically it starts from an input code and ensure that the dependents are not violated, and finally, though the generated code compile time will be used to actually do the actual calculation. So in the compile time here, as you can see, it's starting from an annotated loops, which I will show you in a bit. We have dependence analysis that creates a DAG generation code, and then we have this tile fusion lowering, which actually combine the 2 loops. And then at runtime, once we have all this code generated, we take the sparsity pattern of that matrix, A in this case, and then we create a sparse dependence that we are interested in, and then the scheduler that we created, and finally we run that schedule in the fuse code, and we have the final results. So the code, the tile fusion prototype is implemented in Python using Numba. We implemented as a pass, as a compiler pass, which the input is 2 annotated loop with FP range, as it's shown in here. So these 2 loops are gem and SPMM. So then once we parse the input, create the SSA form, and then we merge these 2 code using a template, a transformation template, tile fusion lowering, I call it here, where we put these 2 codes, these 2 multiplication back to back with some basically loop bounds that are defined at runtime. So basically the reason that we have this is actually causes a conditional statement that actually we can populate at runtime to make sure that actually those iterations that actually are fusible are there. So that's basically what the tile fusion lowering is. And we will see how that T is calculated, which is pretty much the schedule. So the other component in compile time is the dependence analysis. As we discussed, there are we cannot just do the partial fusion anywhere we want. There are certain situations that actually should be met before we do that fusion. And in order to do that, we are analyzing the 2 code. Like we look at the shared data space here, for example, D1, and we look at the read and write instances, read and write accesses, because we want to find read after write accesses, and we want to make sure those won't be violated. So once we have these read and write accesses, we can compute the intersection of them, where it gives us where the read after write dependence at runtime, and then with that intersection, then we can generate an equivalent code to check that condition at runtime. And the code actually is shown on the top over here, which is actually a very naive code because literally it goes over the full iteration space and check whether actually these two equations are equal. But we can do actually much better than this, and the reason for that is because we can simplify this equation over here by just simply knowing that I3 and J3 are fixed iterations, and then we have this constant n, and then we simple symbolic simplification that we use SymPy package, we can actually get this equation where you can generate this code, which gives you with, we can generate that dependence at runtime with O non-zero. So with all of this in place, we can go and see how the code will run at runtime by taking sparsity pattern and run the DAG generation, and then the tile fusion scheduler, and then finally the fuse code to compute the actual calculation. Let's start with the DAG generation phase. So DAG generation phase takes the sparsity pattern of A, as shown in here, and then we run that code that is generated based on the code analysis and gives us this graph over here that the colored vertices, the blue vertices, show an iteration of the first loop, and the white one represent iteration of the second loop, and edges represent the dependence. For example, here we have a non-zero here in the first row, and that causes an edge dependence between iteration 2, the first loop, to the first iteration of the second loop. So having this tag, now we are ready to build our fuse schedule, and that's where we're using the tile fusion scheduler. So we have simply, that's a library call that actually takes a DAG and performs fusion, and the whole, that has 2 steps. I don't want to talk about that scheduler. You can look at our paper. But overall, the idea here is to create this independent workloads that actually has maximum fusion. So maximum fusion means like we are mixing this blue and white vertices as much as possible. And of course, some of them can't be fused. And that's where we have the second, we have this barrier, and we put them on the second, what we call wavefront. So with this, we have our fuse schedule, and we should pass this fuse schedule to the fuse code that we initially lowered, I showed you before. The only thing that I want to add in terms of the fuse code is that we have a bunch of fuse codes that actually kind of comes from the different combinations of these loops. So this is the closed form of the operation, A times B, and then B1 times C. You can see it as A multiply B times C, which is kind of a, could be Einstein notation for tensor compilers. We'll see that. And then here, when A is sparse, then we have B and C are dense. Well, we have gem SPMM and SPMM gem. Those are the loops, kind of, we name it. And then if A and B are sparse, then we are fusing actually 2 SPMM together. So these are the possibilities for the 2 loops that we have studied, and we have results for them. I want to talk about the result briefly. I don't want to go over all the results we have in the paper. We use the CPU, and we also have GPU results. I'm not showing the GPU results here. The end-to-end experiment on the GCN is what I'm going to show you, but feel free to look at our paper about the suite sparse matrices we tested, and also comparing with prior work like tensor compilers and the sparse tiling and communication avoiding method, and each of them actually kind of trying to solve a similar problem with different limitations, advantages, of course. So the end-to-end training that I want to show is the GCN that I discussed initially. So pretty much you can see the layer again here. We want to replace the operation here in this layer with just the gem SPMM, the fused gem SPMM that we created, and we compare it with the based on PyTorch geometric, PyG, to see how it works. And this is actually training, because the the sparsity pattern of A will remain the same for the full batch training on the GCN in PyG. And the results actually was, you can see it in this graph. We have a bunch of graphs which are listed in that table. And the x-axis shows the ID, and the y-axis shows the speed up over PyG. So we integrated both, basically our code into Python to be able to do this comparison. And as you can see, in most cases, actually, tile fusion performs better than PyG. So that's actually a very short presentation of this. Before actually wrapping up this, I want to briefly talk about some of the research that we are doing in SwiftWare Lab with my students, which is actually related to Sparse. So it's good to give you, have that discussion here, well, because all of you are probably working on Sparse. So in the SwiftWare Lab, what we are doing, we are optimizing code and data together. So we have a pipeline of data that look at the data and compress it in lossy or lossless way. Like a lossy is pretty much when we are losing accuracy, and lossless, you can reconstruct the data without losing accuracy. So these red blocks are the works that actually, some of them I will talk about it briefly in the next few slides. And also, once we have that, we have compressed data structure from this compression, which we use it in our pipeline, in our compiler approach. With one of them you saw, the tile fusion. We have enumerated in sparse portion as well, which again, I will talk about it briefly. I will start with the data pipeline. So this is actually a PhD work by Samira, who's led the work. We propose a new data transformation for fusing, compressing floating point data based on entropy information across different bytes. The idea here is when we are dealing with type information, different bytes have different behavior, and we can use that actually to reorder the data, retransform the data, and then we're getting a better compression ratio with the same compression tool. So that's actually for the lossless compression pipeline. We also have lossy compression methods that we use in sparsity to remove some of the elements. Here we are using you're seeing a triangular solve, a sparse lower triangular solve in the conjugate gradient solver. So we have wavefronts. We have synchronization that with the sparsification we can get rid of some of those synchronization. For example, here from 3 to 2, and then we can get performance end to end without losing the convergence. And this is again led by my PhD student Da. And then we have a enumerated and sparse quotient for matrix multiplication, which is actually for GPUs. Here you can see that we are doing matrix multiplication with two different schedules. The color cells show the memory locations that are accessed by each thread in the GPU. The first one is a naive one that we go over 1 down 0 and we do the multiplication. And then we do the thread coarsening on the right-hand side by doing two compiler directives, two unrolling. And then eventually you're going to get each thread we're going to do more operation, and that actually gives you a better locality without losing the load balancing. Again, this is another work led by my PhD student, Hossein El-Bakri. And here is the tile fusion summary. I guess because we are taking the questions at the end, I don't need to give a summary, but I will be happy to take the questions in the panel.